Bryophytes play a subtle yet foundational role in agricultural ecosystems. Their ability to colonize marginal and nutrient-poor soils makes them critical pioneers in soil formation. Mosses and liverworts trap airborne particles, organic debris and dust, gradually converting bare rock or barren land into fertile soil. This initial soil formation is crucial in areas where agricultural practices are planned on degraded or eroded land. Their water retention capacity is particularly important in agriculture. Bryophytes can absorb water up to 20 times their dry weight, which helps in maintaining soil moisture levels. This property is vital in preventing drought stress in crops, particularly in arid and semi-arid regions. Additionally, bryophytes mitigate the impact of heavy rainfall by slowing water runoff and reducing soil erosion. For instance, moss mats can stabilize slopes and prevent landslides in hilly agricultural areas. Bryophytes also contribute to nutrient cycling. Their interactions with soil microbes, such as cyanobacteria, promote nitrogen fixation. Some species, like Anthocerus or hornworts, form symbiotic relationships with nostoc, a cyanobacterium capable of converting atmospheric nitrogen into a form usable by plants. This ability makes bryophytes potential candidates for natural biofertilizers, reducing dependence on synthetic chemical fertilizers. Recent research has explored the allelopathic effects of bryophytes. Certain moss species release chemicals that inhibit the growth of specific weeds, offering a natural method of weed control. Additionally, the antimicrobial compounds produced by bryophytes may protect crops from soil-borne pathogens. These diverse roles underline the importance of integrating bryophytes into sustainable agricultural practices. The medicinal potential of bryophytes has gained significant attention due to their unique secondary metabolites. Bryophytes are among the earliest terrestrial plants. Their biochemical adaptations to survive in extreme environments have endowed them with unique bioactive compounds. These compounds exhibit antimicrobial, antifungal, antiviral, and antioxidant properties, making bryophytes a valuable resource for pharmaceutical research. For example, liverworts are known for their production of sesquiterpenoids such as marchantin and lunularin, which exhibit antimicrobial properties. Marchantia polymorpha, a common liverwort, produces antifungal compounds effective against human pathogens like Candida albicans. Similarly, mosses like sphagnum have been used historically as wound dressings due to their antiseptic and absorbent properties. Bryophytes also produce phenolic acids and flavonoids, which act as antioxidants and anti-inflammatory agents. These compounds have potential applications in the treatment of chronic diseases such as cancer, cardiovascular disorders, and neurodegenerative diseases. For instance, Polytrichium species produce polyphenols that have been shown to reduce oxidative stress in cells. The antiviral properties of bryophytes are particularly promising. Some species have shown activity against human viruses such as herpes, simplex, and influenza. Liverwort-derived compounds are being studied for their potential in developing antiviral drugs for emerging diseases. Despite their medicinal potential, challenges remain in harnessing bryophytes for large-scale pharmaceutical production. These include their slow growth rates, habitat specificity, and low concentrations of bioactive compounds. Advances in biotechnology, such as in vitro cultivation and genetic engineering, are being explored to overcome these limitations and maximize their pharmacological utility. Although bryophytes are not a traditional source of food for humans, their applications in food technology are becoming increasingly recognized. Bryophytes produce polysaccharides, such as pectin-like compounds and mucilage, which have functional properties in food processing. These substances can act as natural stabilizers, emulsifiers, and gelling agents, offering alternatives to synthetic additives. One of the most promising areas of research is the antimicrobial properties of bryophyte-derived compounds. Mosses and liverworts produce a range of bioactive metabolites that inhibit the growth of foodborne pathogens like Escherichia coli and Salmonella. These natural preservatives could extend the shelf life of perishable food items while reducing the need for chemical preservatives. Bryophytes also hold potential as sources of nutraceuticals. Some species contain bioactive compounds with antioxidant properties which can be used to fortify food products and improve their health benefits. For example, bryophytes are rich in trace elements like iron, zinc, and magnesium, making them suitable for developing mineral supplements. Indirectly, bryophytes contribute to food security by supporting the agricultural systems that produce food. By improving soil health, retaining water, and regulating nutrient cycles, bryophytes create conditions conducive to sustainable food production. Research into bryophyte-based agricultural practices could further enhance food security in regions facing climate challenges. While direct consumption of bryophytes is rare, their potential as ingredients in functional foods, natural preservatives, and eco-friendly additives opens new avenues for innovation in food technology. Bryophytes are pivotal in environmental conservation due to their ecological roles and sensitivity to environmental changes. One of their most significant contributions is carbon sequestration. Bryophytes, especially peat mosses, dominate peatland ecosystems which store approximately 30% of the world's terrestrial carbon. By locking carbon in organic matter and slowing its decomposition, peatlands help mitigate climate change. Efforts to conserve and restore peatlands are critical for maintaining this natural carbon sink. Bryophytes are also essential in water regulation. They act as sponges, absorbing and retaining water, releasing it gradually into the ecosystem. This capacity reduces the risk of flooding during heavy rainfall and ensures the availability of water during dry periods. In tropical and subtropical regions, bryophytes growing on tree trunks and branches, known as epiphytes, capture and store rainfall, contributing to the hydrological cycle. As pioneer species, bryophytes play a vital role in habitat restoration. They colonize degraded or polluted environments, stabilizing soils and creating conditions favorable for other plants to establish. Their ability to tolerate and accumulate heavy metals makes them useful in bioremediation projects, where they can remove contaminants from soil and water. For instance, species like Funaria hygrometrica have been studied for their ability to absorb lead, cadmium, and other toxic metals. Bryophytes are also excellent bioindicators of environmental health. Their sensitivity to pollutants like sulfur dioxide, heavy metals, and acid rain makes them valuable tools for monitoring air and water quality. By studying changes in bryophyte populations and diversity, scientists can assess the impact of industrial activities and climate change on ecosystems. In urban environments, bryophytes contribute to green infrastructure by growing on roofs, walls, and pavements. They improve air quality by capturing particulate matter, reduce urban heat by insulating surfaces, and provide habitats for small invertebrates. These functions highlight their role in fostering sustainable and resilient cities.